Hello and welcome to a feedback video, and in this video we're going to look at the current amplifier. Okay, so the current amplifier, also known as the shunt series configuration, and this has to do with our feedback, so the method of feedback and the method of measuring the output. So we'll get to this in a moment. A couple of things that we should know about current amplifiers is a current will rather flow into a small impedance. So with feedback, the input impedance should decrease. With feedback, the output impedance should increase, so that current would rather flow into the load than in the amplifier itself. The gain will be in amps per amps, the feedback factor will be in amps per amps, and current sampling at the output will happen in series, and current mixing at the input side will happen in parallel or in shunt. Right, so getting to the series shunt part, currents are best measured in series if you use a multimeter. So our measurement in our feedback loop will always happen in series, so there will be impedance in here and the impedance inside of the amplifier, and also all the impedances will be summed when we're looking for the output impedance, and at the feedback side here everything is in parallel. So current source should have a resistor in parallel with it, Norton. The input resistor here will be in parallel with this one. The output impedance of a feedback network will be in parallel with everything here. So the input impedance, everything will be in parallel, and the summing of currents also happens in parallel or in shunt. So to look at two examples, let's look at the op-amp side first. Here we have our Norton configuration. So the input with feedback includes the source, and the input of amplifier will exclude the source, but we will be calculating our IF usually. Looking at the feedback network here, a current flows in on this side and it splits into two currents. Okay, if we quickly see this as a virtual ground point, so which it is due to the op-amp. So this current, the output current, will be sampled by using current division. So that is how we will treat our beta network, as a current divider. Also, when we are doing loading factors, we should also remember that we look at current division in our amplifier. Okay, so the loading factors is current division on the input and the output side. Right, so for this problem, we will be looking at the output impedance looking into the MOSFET like this, and there is a bit of a trick to that I will show you. But important part to note for now is the current dividers being used as the feedback network. Okay, the amplifier on this side we can see that we have a common gate amplifier going into a common source amplifier. So this is NMOS, this is PMOS, and everything on this side of a PMOS, this makes it a common source amplifier, since this is the source and this is the drain. Right, so this is a cascade of a common gate and a common source amplifier, and the load will be taken here in the middle. The trick that I spoke about that we're going to have to use on this amplifier will not be valid in this one on this side, since we are using a PMOS. It is better to use PMOSs if you want your mathematics to be a bit easier, but using the NMOS will have a definite increase in output impedance, and the load should actually be sitting up here for this problem, and this ground is just a small signal representation. So typically up here there will be a VDD of some sort um, as well. Okay, something to note is that in most of these problems that we will be doing, the biasing structures is not always included, since we are just trying to focus on the feedback of the amplifiers. Right, but to best explain this, let's do two examples. So we will first do the op amp one and then the double transistor one. I'm also using the MOSFETs here rather um, to exclude all the tediousness of BJTs and having loading effects between amplifiers. But if you're using BJTs, always remember that you will have extra loading effects between amplifier stages, even when you're dealing with the op amp. Right, so your structures will usually look like this, and we did discuss it. So we have everything in parallel on the input side, everything in series on the output side, and remember that we will have current division on the output of our amplifier as well for loading effects. Input impedance should decrease, output impedance should increase. Right, so the rules for finding the gain in the beta network. So your basic amplifier, you will have everything in parallel at the input, everything in series at the output side. For the beta network, you will set up a current source and short the output side, picking the feedback current flowing in this direction. For R11, you will open circuit the output on this side, and for R22, you will short circuit the output on this side, just like we are seeing right here. We have a short circuit, and when viewing from this side, this current source will become infinite and it will be a open circuit. Okay, so the beta is IF over I out, and A is I out over I in. Right, so the problem with the op amp, we will have an op amp with input impedance that's infinite, an output impedance of 1 kilo ohm, but this is not going to matter since we are looking into a MOSFET here. There is no loading factors between the two. So the important part here is the gain of amplifier of 1000. Then the MOSFET here is biased to provide 5 milliamperes per volt, and it has output impedance on this side right here of 20 kilo ohms. Right, so for this problem, let's assume that we have ideal input signal, so its output impedance is going to infinite, and our load, so it should be sitting this side, is 0. So with no loads, the output with feedback is our output impedance, and the input with feedback is our input impedance. So we need to determine the gain of amplifier, beta network, the input and output impedance, and then apply feedback to it to see what our actual values would be. Alright, So for our beta network, we should find the feedback current over the output current like this. So what we see is a current division happening from the output current, and as you can see, the current I chose here and the direction that we need to choose the current when determining the feedback network is in opposite directions. So the answer will be a negative. So the rule with current splitting is we take the current branch that we don't want over the current branch that we do want, or the sum of everything. So we don't want what's in R1. So it's R1 over R1 plus R2. Then we get the current in this direction, but since we should be looking at in a different direction, we have the negative. Okay, so we have minus 1 over 10, and in the end, if we turn this around in the perfect setup, our output should be minus 10 amps per amps. Okay, next, leaving this current source as open circuit, looking into the amplifier in this direction, we see R2 in series with R1, and leaving this a short circuit, looking into the amplifier, into the beta network from this side, we see R2 in parallel with R1. So this was 10k, 90k's, 10k's, and that makes 100 kilo ohms, and the two in parallel gives us 9 kilo ohms. Okay, so anything on the input side, we will be working with R11, and anything on the output side, we will be working with R22. Right, so shunt series. So everything on the input side should be in parallel. So here we have our SIG in parallel with R11, in parallel with RID, which is sitting here on the op amp. Okay, RID is infinite, our SIG is infinite, so our input impedance will be R11 alone, which is 100 kilo ohms. On the output side of this amplifier, everything is in series, but there is a bit of a trick. Okay, we are viewing through a transistor from this side. Okay, so we are seeing R out 1 of this MOSFET right here. We are also seeing R22 in series with it. Right, but we are also seeing this R22 through the transistor. Okay, so the trick when seeing impedances through the top of a transistor is you need to multiply it with the gain of this transistor. So it's the transconductance multiplied by the output impedance right here. Okay, so we have R out 1 plus R22 plus the gain of a transistor multiplied by R22. There is a chapter in the book for this. So which is a bit more advanced. Make a different video at some point to explain all of this, but this is actually just feedback that happened twice in the same problem. So whenever you have NMOS like this, and the load should be taken up here, actually, always remember to include the impedance of the transistor and the resistance seen through it, like this. It has a huge increase in impedance as you can see. So this approximation down here you will see in a lot of places. This R22 is much smaller than any two of the other factors, so it is reduced and R out 1 is taken out. And this down here looks like the 1 plus GM R22 that you will have a um, common source configuration. Right. Okay. The next step would be to find the gain of this amplifier. So first, let's ignore the input right here and focus on that into this amplifier we have a voltage input and then a differential gain of the amplifier. So, and we are inserting on the inverting terminal. So for the op amp we have minus AD times the input differential. Then there is no loading factor between the two amplifiers. The MOSFET right here, if we are looking at a load resistor sitting up there, we have a transconductance of our MOSFET divided by 1 plus GM R to 2 parallel in R out to R out 1. So this is the gain provided by our MOSFET. So if you add R load here, then it's a common source amplifier like you're used to, but we are just more interested in the transconductance at this point. And then lastly, to find the output current is we want the current flowing in these feedback resistors right here. So R22, since it will be the same flowing in a load resistor up here, we have current division. So we don't want the current flowing in the MOSFET, so that is R out 1, but we do want the current flowing down here in these resistors since everything is in series. So we have R out 1 over R out 1 plus R22. That is the current division on the output side. Right, for the input, we picked a voltage sitting here on the input side. So if we need to convert that voltage to a current, the input differential current is the input current multiplied by the input resistance. Okay, so Ri comes in really handy here by using Ohm's law. So now we can just replace VID with Ri, and we have our current gain right here. Okay, so those two will go away and we will have I out over II and our current gain calculated, and that's almost minus 11,000 amps per amps. Alright, so if we have those three things, we can calculate our input impedance with feedback. So the input should decrease, and that becomes 91 ohms roughly. The output impedance should increase. That will go to 1 gigaohm or 1000 meg. And the current gain minus 9.99 amps per amps, which is close to the minus 10 of our feedback factor. And that is our first example. The second one would be our common gate into our common source amplifier on this side. And luckily this one, if the load is sitting on this side of the amplifier, so we won't be seeing anything through the amplifier on this side. Right, so this problem will be a little bit more normal versus the previous one, since we are using a PMOS right here. Okay, the feedback network is exactly the same as the previous problem, so this will be again for minus 10 amps per amps. The two transistors is biased at the same transconductance, so 5 milliamperes per volt, 5 milliamperes per volt. Output impedance of both is at 20 kilo ohms, and we need to find all the factors: the gain, the feedback, the input, the output, output, and gain with feedback applied, and then the output impedance without the load. Okay, so feedback network is the same. R11 is 100 kilo ohms, R22 is 9 kilo ohms, feedback factor 1 or minus 1 over 10. So not much has changed for the feedback network. Right. On the input side, we should look at everything in parallel. So the impedance we see looking in here is 1 over GM1, and looking this side is 100 kilo ohms. Taking that in parallel will give you almost 200 ohms. On the output side, the impedance of our PMOS plus our load plus R22 will give us 50 kilo ohms. And where is our input and output impedance? Done. Okay. There is no loading factor between the two amplifiers, since it is a MOSFET. If this was a BJT, there will be a loading factor that you need to take into account here as well, and it needs to be multiplied in this final gain equation right here. But let's have a look at our two amplifiers separately. Okay, so the input current flowing into a common gate amplifier or a common base amplifier, the current on this side is the same as the current on that side. So a common gate configuration is also known as a current buffer. So the current input here will be flowing in this resistor right here, and if we want to take a VGS of this transistor, it is sitting on this side right here, and it is in common source configuration. Right, so the VGS of this transistor is the current flowing in this resistance right here. So VGS2 is equal to IIRD. So this transistor is just acting as a current buffer. And that is what a common gate typically does. It buffers currents. You can do this problem with a voltage amplifier configuration. So this will be GM1 multiplied by this transistor right here, and then you have to do the conversion of a second transistor, and it will get hairy quite quickly. And then you also need to include some of our loading effects as well. Okay, this is by far the simplest way, is just seeing that, oh, the current flowing here and the voltage here should be the same, and the current is being buffered. Okay, the output current flowing in the low down here is due to the transconductance of the second MOSFET. So I out is minus GM2 VGS. So the voltage being applied here multiplied by the transconductance is what current we will have flowing out of this transistor. Okay, so the total gain of the two would be minus GM2 RD. That is the total gain of this without any loading effects. Then we need to look at the loading effect on the output side and the loading effect on the input side. So on the input side, we have a current flowing in that direction, so 1 over GM1, and the current flowing in this direction, the one that we don't want, are 1, 1. Okay, so we have current division on the input, and we want the current flowing up into this MOSFET. So that is why it's one sitting down there. On the output side, we have a current flowing in the MOSFET, which is the one we don't want, so R out 2 over everything else. So R load and R22 is in series with one another. So we want the current flowing in the load and the current flowing in R22 would be exactly the same. We don't want the current in the MOSFET. So R out 2 over R out 2 plus R22 plus R load. And that is our two loading factors or our two current dividers. So minus 100 output loading factor, input loading factor, the total is minus 66.87 amps per amps. Right, so this value should decrease, this value should increase, and our gain should settle to something close to minus 10. So decreasing our input impedance gives us 26 ohms. Increasing our output impedance gives us 231 kilo ohms, and our gain finally would be minus 8.7 amps per amps. Everything on the output happens in series, so our output with feedback is our output impedance plus our load, and that gives us 250 kilo ohms output impedance. And that is current feedback amplifiers. So remember, this is current division. You will have current division on the input side, you will have current division on the output side, and everything will work out fine. Okay, and that's it for the shunt series configuration. Thank you for watching. I hope this makes feedback much easier for you.